Assalamualaikum. My name is Rameen Khalid, and the topic of my presentation for quantum paper is quantum theory of solids, and I have chosen lattice vibrations. As we know that a lot of research has gone into vibrations of one-dimensional lattices. This is the how phonons got into existence in quantum theory. In order to study the behavior of phonons, many hypotheses were to be made. This In this paper, I have solved some dispersion relations for one-dimensional lattices. Dispersion relations are of a very significance because they allow us to calculate the velocity with which a wave moves in medium as a function of frequency. All we know about phonons that they are a quanta of lattice vibrations. They play important role in various solid state physics. So the physics of phonons and phenomena associated with them are I have explained in this paper. The term phonon is used to draw an analogy between photon representing a quantum of electromagnetic radiation and quanta of lattice vibration. So, theory of phonons explains mostly solid state phenomena, which cannot be explained with static lattice theory. As we know that all solids have periodic array of atoms in a crystal, except the amorphous solids, the existence of periodic crystal lattice in solid materials provides some medium. Between the lattice spacing, there are quantized vibrational modes, which are called phonons. And their study is really very important as they allow us to understand that how energy is to be calculated, how energy be calculated, and whether it is electrical or thermal to be absorbed in solids. So phonons are also quantum mechanical version of special type of vibrational motion. So this type of vibrational motion is called normal mode, which is a pattern of motion in which all parts of system move in a sinusoidal fashion. So as we know the framework of one-dimensional monatomic lattice, as we become familiar with the scattering connection of one-dimensional lattice, thereafter the procedure for diatomic will be seen according to the monatomic. So they are basically the massless quantum mechanical particles, and they behave like particles in k-space, and they also are called the quasi-particles. So what is the example of normal mode will be? Example of normal mode in standing wave will be that all the coordinates of normal modes and all space elements xyz coordinates are oscillating at the same frequencies and phase, but they have different amplitude. Now the types of phonons, one is optical and other one is acoustic. Optical are quantized mode of lattice when two or more charged particles in a primitive cell move in opposite directions. This mode has highest energy for wavelength infinity, or we can say that k equals 0 when the two lattices move in opposite direction. And optical phonons have a non-zero frequency at a Brillouin zone center. This is because they correspond to a mode of vibration where positive and negative ions at adjacent lattice sites swing against each other and creating a time-varying electrical dipole moment. Another one is acoustic phonons, and they are the one whose frequency which goes to the zero in the limit of when k is really very small. Now what are lattice vibrations? Lattice vibration is the oscillation of atoms in solid about equilibrium position. For some crystal, we can say equilibrium position form a regular lattice due to the fact that atoms are bound to neighboring atoms. and the vibration of these neighboring atoms is not independent of each other. And it is a periodic array, and particles are identical sphere of same mass. Atoms in solid vibrate because of their thermal energies or some external energies we can provide to them. Now we will consider lattice vibrations for monatomic case. So we have taken some dimensional chain of atoms, that is one dimensional. All atoms are similar. They have same mass and equal distance between them. The figure is showing that the forces between atoms in this lattice are proportional to the displacements. So it is resembling some harmonic approximation. Now we are considering the entire chain of atoms. If u subscript n is the displacement of nth atom, then within its elastic limit, then what will be the elastic limit? Then force is proportional to displacement. Then force on nth atom due to n minus 1 and n plus 1 atom will be k un minus 1 from left, and k u subscript n plus 1 minus un to the right. So the net force will be equation number 1, F subscript n, and in this equation D is interatomic force elastic constant. So applying the second law to nth atom, we can get the equation number 2, where m is the mass of the atom. Similar equation can be written for the atom in the lattice, other atoms in the lattice. Now we have the solution of the form equation number 3, and x is the equilibrium position of nth atom, and we can consider that x equals Na. So this equation represents a traveling wave in which all the atoms oscillate with the same frequency and same amplitude and have a wave vector k. We can substitute equation 3 in equation 1, and e to raised to the power ikna will be the common factor, so it will be cancelled. So dispersion relation for frequency for monatomic case will be equation number 4. This is the what is dispersion relation? It actually relates frequency with a wave vector. So this is the dispersion relation. Now we can see this in graph, this dispersion curve, it clearly showing that for one value of omega we can see several values of wave vector k. First Brillouin zone will be from minus pi k by a to pi. We can multiply a with pi on the both sides, we can get the wave vector k. Second Brillouin zone is minus 2 pi k by a to minus pi. So this is the limit of first Brillouin and second Brillouin zones. Now we can take the different cases if frequency is low and high and maximum. First of all, if the frequency is very low, then k will be approaching to 0, and dispersion relation will reduces to omega equals omega max ka by 2. So we get our phase velocity and group velocity relations, which both will be equals to vs. So in this discrete chain of atoms, the dispersion relation is linear if it is as it is continuous. So both will be equals to Vs, and this is case if in fact long wavelengths in the system do not respond to discreteness of the system. So here a very large number of atoms contribute to displacement, which is much similar to case of homogeneous line. And in this case the dispersion relation will be linear. Second case is frequency of oscillation will be high. In this case we get our phase velocity and group velocity relations as follows. It is clear from above relations that both group and phase velocities are a function of frequency omega max. This kind of medium is highly dispersive. In the previous case the medium was not dispersive, it is followed the characteristics of homogeneous continuous medium. So in the next one, if the frequency of oscillation is maximum, then we get our phase velocity as 2vs over ak and group velocity is 0. The 0 group velocity refers to no propagation of energy or signal. In this case only standing wave is produced. Now the diatomic one-dimensional lattice vibrations. The one-dimensional diatomic lattice will be look like this, where we have taken mass m1 and m2. They are of different masses. So we can get equations of motion for this case, which is shown in the figure below. M1 u subscript n with a double derivative, that is after applying the second equation of motion, that is F equals ma. And the equilibrium positions of these two atoms of mass m2 are indicated by black and white circles. So and displacements are un and vn at the given instance. Now, like a monatomic lattice, we are looking for solution of traveling mode for the two atoms diatomic lattice. If we consider that all atoms vibrate with the same frequency omega, and we can write then solutions of equations that follows, which I have written u2n plus 2 and plus 1, and then their double derivatives ahead. Now we can get the dispersion relation, a final dispersion relation for diatomic chain, as equation number 7 is showing. So when the space vector is really very small, we can get the equation number A for optical frequency for the optical zone, and for the acoustic zone in the equation number B. And at the edge of the brilliant zone, when k equals pi by a, we can get the equations C and D for optical and acoustic respectively. The lower curve in this figure is called acoustic branch, while upper is optical. Optical branch begins at k equals 0 and omega equals 0. Then with increasing k, the frequency increases in a linear fashion. The distinction between acoustic and optical branches at lattice vibrations can be seen most clearly by comparing them at k equals 0 and wavelength is infinite. The molecule oscillates as a rigid body for the acoustic mode, and for the optical oscillation takes place in such a way that the center of mass of molecule remains fixed. The two atoms move in and out of phase. A frequency of these vibrations lies in infrared, so for that reason they refer to as optical. So to conclude, we can say the lattice vibrations are quantized, where quantum of lattice vibration energy is known as phonon. Atoms in chemistry cannot vibrate with all frequencies. There are some definite frequencies with which the lattice vibration can exist, and these frequencies exist in the form of a lower band of energies. For one-dimensional monatomic chain, the dispersion relation is linear in the long wavelength limit, whereas in the higher frequency region, the medium behaves as a dispersive one. For diatomic linear chain, the frequency range is split up into two frequency branches, optical and acoustical, where frequency of acoustical branch is less than optical. The region between optical and acoustical is the spectrum is known as forbidden frequency gap, whose width increases with the increase in the mass of that. Thank you.